Hi, my name's Hugh Possingham, and I'm going to talk to you a bit over the next 30 minutes about how much I think decision science means to the field of conservation biology. I'm the Chief Scientist of the Nature Conservancy. The Nature Conservancy has over 300 scientists that assist the entire organisation, working in 70 countries, to deliver outcomes for both nature and people. And decision science is a very big part of our work. But what is it? So I'm going to talk about what it is, how it's much simpler than many people think. I'm also going to give some examples of what I think are important issues around decision science, and I'm going to tell some stories about how I came to think that decision science was very important for conservation outcomes. And finally, I'm going to briefly discuss why we've created the Environmental Decisions Alliance that is currently chaired by Dr Eve McDonald-Madden. So what is this thing, decision science? Firstly, it's not really even a science. It's really an approach and a methodology. It's a very open toolbox about how we can go about making better decisions to deliver better outcomes for nature and people. So this is my slide of life, and this is where, instead of you having to read a book or hundreds of papers about what decision science is or what decision analysis is, I've just boiled it down to 6 things and 31 one-syllable words. And it's basically how you run your life. You can use this to decide whether to take an umbrella to work. You could use it to solve a conservation problem. You could use this slide to work out how to run the transport system for a city. You could use it to choose who should be your life partner if you want to. Firstly, you've got to have an objective. So what do we want? What do we or a group of people want? And this could operate at the scale of a small, tiny reserve, where there's just maybe a handful of people involved in deciding what they want in terms of habitats and species and amenity. Or it could be an entire nation. It could be a huge government deciding what they and their people want to achieve in the landscapes that they manage and control. Setting objectives, getting what we want sounds a very easy thing to do. In many ways, it can take months, if not years, in most circumstances. The second part of decision science is what can we do? What are the actions we can take? So this is a little bit less contentious. It's a matter of looking down and thinking, what are all the things I could possibly do, and listing them. If we're managing a small park, it could be, should I be managing herbivore density? Should I be putting up a fence? Should I be rerouting some of the trails? Should I be using herbicide, and how much to get rid of what weeds? What are the list of actions we can possibly take? The third part is linking that set of actions to the set of objectives. Maybe we have one, maybe we have several objectives. So this is really, how do the things we can do change what we want? And this is really just modelling. It's a prediction of the future. If I do X, what will happen to A? If I do some weed spraying, what are the consequences for the things I care about? The weeds, the native species that are there, and the impact on the weeds that then affect the native species. Once I've made all these models, and that can be a time-consuming and fairly technical task that link the actions to the objectives, the fourth step is to work out what are the best things to do for this small park. What are the most cost-effective things to deliver the outcomes I care about? Do I care about dog walkers more than other things? So shall I take those actions that are more important for dog walkers? Do I care a lot about butterflies? Maybe I set that up in my objectives. So what are the actions that will deliver the best outcome for butterflies? Or do I care about a mix of actions? So this is really what a mathematician would call the algorithms. This is the tools that I and my lab have liked to build, including the software Marxand, that actually turns your hopes, dreams and fears, the objectives, into actions that are the best actions to do to deliver those outcomes that you want. So once you've used the algorithms and you've decided as a community the kind of things you want to do, of course, then you've got to do it. And that's not enough, because many of the things we've decided are very uncertain. We be uncertain about the objectives. We may learn new actions as we go along. We may even change what we want. So all the while we're doing, we're also learning. And so that's it. That's decision analysis, that's decision science. It's not very complicated. I know that many people like to make it complicated because economists have jargon and mathematicians have maths, and maybe consultants want to make a lot of money, but it doesn't have to be that hard. Anybody can do it. So why did I come to a point in my life 25 years ago when I suddenly woke up in the morning, actually 30 years ago, thinking that decision science was what I wanted to do that can be most useful for conservation? So this is a bit of a long story. In the late 1990s, I was at Australian National University and I was working on conservation problems. So in the late 1980s, I'm not that young, 1980s, I was a postdoc at Australian National University. I was working on conservation problems with Ian Noble, but I got involved in the forestry debates in Australia. First of all, I started to review some conservation plans for the southeast of New South Wales, and as I was reviewing those conservation plans, I started to look into the mathematics of conservation planning, which Australia in many ways had led through CSIRO and people like Bob Cressy and Chris Margils. So I looked at the decisions of conservation planning as they apply to forests, and I saw there was a lot of mathematics in there and there was a lot of decision science. Which bits of the forest should be protected from logging? What kind of logging should we do in different places? And I realised that many of the planners didn't know a lot of that decision science. So I started looking into the maths of reserve design. From there, I went to a mathematics department at the University of Adelaide. There, I was fortunate enough to teach optimisation. I knew nothing about it to third-year students. They probably taught me more than I taught them. And in that process of teaching optimisation, I broadened my tool base. And in fact, during my PhD, I had worked closely with Alistair Houston and John McNamara, and I'd learned a lot about optimisation and decision science through the lens of a behavioural ecologist, trying to work out whether animals were optimising their behaviour or not. Dynamic programming methods, linear programming methods. So I'd done some practical problems with animal behaviour around optimisation. I then had to teach optimisation to third years who kept me honest. And more I was getting interested in reserve design. But in fact, reserve design and spatial planning was the one area where conservation scientists were doing a very good job at applying decision tools to conservation problems. I then realised that, in fact, maybe we weren't doing a very good job in so many other areas. So let me introduce you to two of my friends and another issue that made me realise decision science is something that we need to embrace more widely. These two friends are very similar. Leadbeater's possum, David Lindenmayer. You might say, are they very similar because they're cute and they're furry? Mainly they're very similar because they love forests. So David Lindenmayer and I, through the same contentious issues around forests, had been asked by the federal government to start to look at the viability of Leadbeater's possum, but many other species, not just in these beautiful mountain ash forests as Victoria, but also how could we create a toolbox through population viability analysis to get a much better understanding of how the forest needed to be managed to create viable populations of this unique animal, Victoria's only endemic mammal. So I did something that I like doing, and that's building population models. And we built those population models. And as we built them, of course, a lot of the time in population viability analysis, you ask a fairly esoteric question, that is, what is enough to make this species viable? But in the end, I realised probably that isn't the right question. That is a question about an almost an unanswerable question. Let me go through some of the analysis we did. And the analysis we did, in fact, was very much constrained by the social and economic circumstances in which we found ourselves. Imagine a compartment of forest, maybe 6,000 hectares large. Basically, at that point in time, in the early 90s, they weren't going to close down logging in mountain ash forests of Victoria. So we were told, give us a realistic plan. Give us a plan that gives us the best chance that leadbeater's possums will survive within a reasonable set of constraints. So firstly, we ran lots and lots of population models, complicated population models. I killed millions of leadbeater's possums in the computer and millions were born. And we discovered things like stopping salvage logging would cost virtually nothing to the industry, but would deliver great benefits. But then it came back to the idea of what else could we do? And we thought that, well, maybe we should explore the idea of some small reserves in these forest blocks. So imagine 6,000 hectares. And then the question is, if we could set aside 10%, and that might be realistic economically, should that 10% be one 600 hectare reserve, 6 100 hectare reserves, or 24, 25 hectare reserves? So we ran the models and we worked out the probability of extinction under different circumstances. And these are the kinds of results we get. And if you look at that, you say, okay, this is good. If the reserves are highly fragmented, then the chance of extinction is too high. If there was only one big reserve, the problem is that catastrophic fires are very likely to wipe it out. The reasonable balance is something like a 75 to 80 hectare reserve. So that's good. The probability of extinction was maybe 30 or 40%. But, there were lots of uncertainties about this modelling process. There were lots of uncertainties about how easily leadbeater's possum could move from patch to patch. Well, David and his colleagues had done an enormous amount on the ecology of the species. There were still many things unknown about this very cryptic little animal. So given those uncertainties, and particularly given uncertainties about fire, we actually ran the models even more and found that if you accepted those uncertainties, we came to the dramatic conclusion that the probability of extinction of leadbeater's possum is a number that is between 0 and 1 inclusive. So there's so much uncertainty, we have no idea whether leadbeater's possum is doomed or it's safe. But what we then also did is we added some of that uncertainty and said, well, what if the fire frequencies were enormously higher? If the fire frequencies were enormously higher, then yes, the probability of extinction went up a lot. But maybe that doesn't really matter, because we can only do what we can do. You wake up in the morning and you do your best. And the amazing thing was, even though if we included this uncertainty, if we added in a lot more fire or had a lot less fire, if we changed the movement rates, the bottom line is that the optimal reserve size stayed somewhere between 50 and 100 hectares. And so the decision we had to make was incredibly resilient to uncertainty, even though the outcome was very, very sensitive to the uncertainty. And this is a really important point that made me realise that the question we'd be asked, give us a plan to save leadbeater's possum, was not the right question in this set of circumstances. The real question was, given the constraints that we had, the socio and political constraints and the ecological constraints of the system, could you please deliver us some outcomes, some management options that gave this species the best outcome it could possibly have? And at that point, I was on a study leave break at Imperial College in London. I was actually out at Silwood Park. John Lawton was mentoring me there. And I remember the day, I remember the morning when I thought, this use of decision science that we had applied in conservation planning, that is widely used in fisheries and pest control, there were literally hundreds of interesting problems in conservation which had never had a decision science lens focused on those problems. And that is what I started to do. Uncertainly at first, because I was puzzled why we hadn't used decision analysis for so many conservation problems. And in fact, I also realised that so much of classical conservation theory was just not very useful. These issues of what is a minimum viable population size? Well, maybe it doesn't matter. Maybe we just do the best we can under the constraints we have. A lot of people were still doing reserve design, and they ignored the cost of places when they planned for those reserves. They ignored a whole heap of socio-economic factors when they planned reserve systems, and they even ignored issues like connectivity. We asked questions about which species are more important, and we did a lot of mathematics about phylogenetic distinctiveness, but basically nobody particularly cared. And just because something's phylogenetically more distinct does not mean it's the most important species to work on, let alone how threatened it is, let alone whether it's useful in a food web or not. So I sort of started to realise that so much of the conservation literature was telling people what to do, number 5 on that dot point of things, what to do, telling people what to do, but they were ignoring all the decision science literature. They were ignoring it entirely. And so we started reframing a lot of these discussions and debates. A classic example, again, was global biodiversity hotspots, first started in a landmark paper in 1988, and then followed on by many, many organisations, environmental NGOs, creating maps of what were priority places for conservation around the planet. When we look at them very carefully, you realise that those maps are certainly far from operational, because they ignore a whole heap of important issues like, are those places threatened in the future? What is the cost of acting in those places? Indeed, the key thing is, in general, we didn't even know what the action was. There was this vague notion that we'd be protecting those places, but wasn't clear what kind of protection that would be. And we also had very little idea of how successful those actions in those places would be. Should we be restoring in those places? Should we be doing sustainable farming in those places? Those global biodiversity hotspots were maps that clearly had no actions and therefore were far useful than they could have been. So let's remind ourselves what the 6 things are. In all these problems, we really need to be clear about our objectives. And so many of the problems are single species problems, which might be minimise the chance of extinction or maximise the mean lifespan of the species. But also it makes you think about, maybe we're interested in maintaining abundance above a certain level, if this is a useful species like a pollinator. What are our objectives at the landscape scale? Now we've got to think about a representation of different habitats. We've got to think about protected area systems and management actions that conserve many species simultaneously. We need to think about ecosystem processes, ecosystem services, and many things. So our objectives can be quite broad. Amalgamating them into 1 or 2 things then becomes very important, because if you try to maximise a dozen things, the problem becomes complicated, because you need a whole series of inexplicable and hard to explain weighting factors that balance those objectives out. When we also start to think about actions, we realise there are so many different actions we can apply in different places. And in fact, some of these actions may be policy actions, some of these actions may be education actions. So have we ever looked very carefully in a country or a state or a region, how much effort should we be putting into education? How much effort should we be putting into policy reform? How much effort should we be putting into actual on-ground actions? How much effort should we put into changing the market forces that drive land use? How much effort should we actually just be buying land and conserving it ourselves? And then, of course, the bit that we, as a modeller, love is connecting all those actions with all those objectives. And then the other bit that I love is the algorithms. You know, what are all the tools that we can use? What's the maths behind choosing between the actions that deliver us reasonably good objectives and reasonably good outcomes? And of course, as we go through doing and learning, there's a whole rich set of modelling and mathematical tools that we can use, and that often comes under the frame of active adaptive management. So the more you look at this framework, and the more you look at the conservation problems we have with pests, with invasives, with restoration of habitat, with eutrophication, you realise that there are literally hundreds of unposed and unsolved decision science problems in the world of conservation, and that's kept me highly amused for the last 25 years. The first sort of content thing I'd like to talk about, rather than just babbling about why I'm so excited about decision science, is that one of the algorithms that I find incredibly effective, which requires almost no mathematical skill and solves many, many problems, about 90% as well as it can be solved, is what I call the shopping formula. It's the formula of cost effectiveness. And in some senses, whatever scale you're at, one of the simplest things you can possibly do when you're given a range of options and actions and strategies to evaluate is just to look at each strategy, try and calculate or estimate the expected net benefit of carrying out that strategy over a period of time, add in some factors then that change the probability of success. So is this a place or this is an action where the community or the economics mean that it's unlikely to succeed? So estimate that probability of success and then multiply those two things together, and then therefore you get the expected total net benefit. So there's a package of actions or a strategy, a project, and you get this expected net benefit of that project. And then simply divide it by the cost. That is the cost effectiveness of that strategy or package of actions, and then look at how that relates to other strategies or packages of actions and see which one seems to be far more efficient than the other. Now, there's always going to be ancillary things, but if one action is 100 times, delivers 100 times the expected net benefit per unit dollar as another, it's hard to ignore that when you're making decisions. And this really builds on some of the work that's been done around conservation evidence, for example, where people are saying, how can I improve this stream? Should I need to put some structure into the stream? There's many ways you can put structure into a stream to improve habitat quality. One is you could just go along the banks and grab and chop down a few trees and grab a few logs and throw them in the stream. Coarse woody debris, hung it in the stream. The other one is you could do a whole heap of engineering solutions with concrete. Now, I think in the past we may have found that the concrete option is far more effective. It could be 2 or 3 times more effective. But if throwing the wood into the stream is 20 times cheaper, then maybe throwing the wood in the stream is the thing to do. And so cost is a really important factor that ecologists seem to want to ignore in many of their strategizing and much of their use of actions. So if you do nothing else, I urge you to just use cost effectiveness as a way of ranking and sorting through options and actions for any purpose at any scale. It's not perfect and ignores a whole issue, many issues of dependencies and complementarity, but it's not a bad start. My second bugbear at the moment is that we have in the past years produced many maps of conservation assets. Now, mapping conservation assets such as habitat, species and ecosystem services is absolutely essential, and we're getting better at it and we're getting smarter at it. We're delivering it more cost effectively. We have a lot of species data. The revolutions in species distribution modelling mean that data becomes more and more accurate as time progresses and we get more data on species. But so often I've seen in my life people presenting a map of the species richness or the number of threatened species or the amount of some other asset like wilderness or carbon sequestration potential, and delivering that asset and then implying that tells us what to do and where to do it. Well, first of all, we often don't know what to do. So you can only conserve an asset through actions. If you don't know the actions, you don't know the cost of those actions or the probability of success of those actions. So these asset maps have to be put in because they tell you that top bit of the formula. They tell you the expected net benefit of doing an action in a place. But the asset maps per se tell you nothing about what to do. They tell you nothing until they're combined with some ideas about what actions you could take, the costs of those actions, and the probability of the success of those actions. And so the Nature Conservancy is rapidly moving to a situation where we're going to still do asset mapping and we're going to still do threat mapping, but we need to now do action mapping. So the map that tells the politician or managers or us indeed what to do where, what are the most important things to do in a particular place, we're going to call them spatial action maps. They combine all that information and actually are likely to deliver outcomes far more cost effectively than just observing a map of species richness. So sorry, I get a bit overheated when I talk about asset maps and action maps. So as you can see, I think there's just a lot of work to be done. When early 1990s, it dawned upon me really quite late that decision analysis and decision science, that they were the path forward that could help us to make a better world. It's been a long haul. We've built tools, we've built ideas, we've built processes, really that, to be honest, we've stolen from engineers, economists and mathematicians, but we've translated them into on top of the problems that concern conservation organisations and governments and communities who care about the natural environment. But we have a long way to go. A lot of those tools were clunky. A lot of those tools were poorly interpreted. A lot of those tools were not well managed and delivered outcomes that superficially seem ridiculous. Therefore, they're not entirely trusted. So there's no doubt about it. The path to bringing decision science and decision analysis to conservation has been a very, very rocky path. However, I now feel as though there's enough of us and to make this process a whole heap better, a whole heap less mysterious and a whole heap more useful, so that we can conserve nature and deliver outcomes for people. And there's a whole heap of people who seem to agree, and Eve McDonald Madden has gathered those people together in an organisation, a very loose organisation called the Environmental Decisions Alliance. You can go there to the website, you can join this alliance, you can be informed about it. There'll be a series of webinars, maybe one day there'll be a conference. The other webinars will be much better than this one. They'll be coherent, they'll be well prepared. But I suppose I'd really just like to say, join us in the journey. You may be already a believer. If you're too obsessed with it, then maybe become a bit less obsessed. If you are a disbeliever and you're highly cynical, tune into some of the webinars, find out what we're doing, ask us some questions, and in the end, we hope that the planet will be the benefiter of all our work. And that's enough from me.